parent company who's just producing I've been working on IGCC, and they are in line for 300 megawatt demonstration plant in Korea, operational in 2015. So just setting the scene. Another probably main announcement. The talk was supposed to be given by Swaminathan, who's our principal engineer for fossil fuel technology. Unfortunately, because of other work commitments, he was not able to be here. And since I'm coming over for the post-combustion capture talk, would you mind moving on? Sure, I'll try to do justice to it. So, any questions? I'll try to answer the best of my knowledge and understanding. Anything else, I'll be more than happy to take it back to Jerry and get back a response to you. Okay. Just to give you a slight background regarding the company, Doosan Power Systems' vision is enabling energy to realize opportunities for customers and world we live in, which basically means we are a customer-oriented organization, and we provide what we need with whatever we have in hand. Typically, any work that happens at Doosan Power Systems is based upon four kind of fundamental rules. One is being bold, and at the same time being pragmatic or practical. At the same time also being committed to what we want to deliver and collaborate. So those are the kind of four pillars for the work that we do at Doosan. Just to give you a brief heritage lesson, Babcock and Wilcox Energy has a long history. It started in 1891, where Babcock Power and Babcock and Wilcox separated in 1979. And there, after an acquisition by Mitsui Heavy Industries, Babcock Energy became Mitsui Babcock, and then in 2006, Doosan took over and it became Doosan Babcock. And from 2006, over a series of strategic acquisitions, we've grown to become Doosan Power Systems. And the two main acquisitions, one is on the steam turbine side, which was Skoda Power, who have a longer heritage in the power plant industry in the Czech Republic, and they as well went through a lot of series of transitions and joined. They were acquired by Doosan to form Doosan Power Systems. And recently, last year, we acquired Lenchus, and they're part of one of our business units. So just to give you a feel for how the company is split up, in a sense is Doosan Heavy Industries is our parent company, and Doosan Power Systems lies under Doosan Heavy Industries. We've got a lot of employees, as you can see, and about 400 to 450 in the research and development in various parts of the business. Doosan Power Systems is kind of split into four business units, profit and loss making units. One is for boiler and air pollution control, where Doosan Babcock and Doosan Lenchus fit into the picture, and oxy-fuel development is actually part of this business unit. Skoda Power, as I mentioned earlier, is suppliers for steam turbine. The plant business group was a recently new creation in the company with a drive towards going to EPC turnkey projects. So plant group is the integrator of all the components when it comes together. And because carbon capture is in its nascent stage, carbon capture sits under the plant business unit. Carbon capture as post-combustion capture. And then, as other OEMs, we've got a service business unit, which is very handy. Just to give you an outline for the talk for today, just want to go through an overview of oxy-fuel technology. It won't be complete if I don't probably give you a little bit feel about the air separation unit and the CO2 purification and processing side of things as well. Just want to mention that section is actually adapted from Air Products presentation that they did last year. So I'm going to give it for you for the sake of completeness. And then we go into detail about the proof of concept testing that we've done, the demonstration of the oxy-fuel combustion system, which you've heard about, which is the world's largest 140 megawatt terminal at Renfrew. And then we'll give you some key points on the thermal performance that we've identified, based on some studies as well as some background about what kind of design tools to be used in the company. And plant demonstration is going to talk about a couple of significant projects that we've been part of and provided a commercial bed performance guarantee, etc. fancy when we talk about high purity oxygen and high purity CO2 environments. But that's something that we've addressed over the course of years. Just a background about oxy-fuel technology, as Francisco spoke about the IPCC today morning. The other form of carbon abatement technology is oxy-fuel, where instead of burning the coal and air, separate the nitrogen out, and you burn it with relatively pure oxygen, CO2, and coal. And the oxidant or the CO2 or the oxygen that we talk about here is about 95% pure oxygen that we consider as an oxidant. It's not to be confused with the oxygen concentration in the boiler, because the recycled flue gas is also recycled to connect to the combustion air, primarily to moderate the high temperatures that we experience with high oxygen concentration. So, and we also want to replicate radiant heat transfer as in air firing, so that you don't have to go through a lot of changes on the pressure flux elements in an oxy-fuel boiler, and also maintain the volumetric flow rate, which is critical when you want to consider the negative heat transfer. Just for the output from the oxy-fuel firing stage is you get about 75% volume of CO2, so it's primarily CO2 and water. As you're aware, oxy-fuel works on the principle that we actually separate the nitrogen prior to combustion, rather than as in post-combustion capture, where you actually do the separation after the combustion. Just to give you a schematic of the oxy-fuel combustion process, you're probably very well versed. So air coming in is going into the air separation unit, nitrogen is taken out, oxygen and the recycled CO2 into your boiler, connected to your steam cycle, particles, condensation, sulfur removal, condensation, and CO2 for purification and compression. If you just don't look at the side of the air separation unit, the rest of the sketch looks like an exact boiler. So you're not making any changes to your process. You're not messing about with the steam cycle as you would in a post-combustion plant, in a post-combustion carbon capture plant. This slide, the purpose of the slide was try to address some of the questions that have come up yesterday. Today morning was about what's the net power output. These numbers are from a DTI project 407, which was funded by the Department of Energy and Climate Change in the UK. And what they basically have done is provide a comparison between a normal air-fired unit, which is the baseline, and an oxy-fuel, as to show you what is the power consumption throughout the plant, as well as what is the net power that you actually can send to the grid. So if you generate the power is in the ballpark of 625 megawatt, when you are doing your conventional power plant, you do for 50 megawatt on your auxiliary power, and you can send 576 or 575 to your grid. But when you do oxy-fuel capture, you have two additional penalties or two additional points where you need to provide energy. One is the air separation unit, and second, CO2 compression, to take it from whatever pressure you're at up to at least 150 bar to actually send it to your pipeline. So those two are critical power consumptions by oxy-fuel plant. What these numbers technically correspond to is very similar to what John and Francisco mentioned, is 9 to 10% loss in efficiency points on a net power plant, which is very similar comparing all the carbon abatement technologies, keeping in mind the assumption is you do 90% capture. Reduce the percentage capture, reduce the delta, but that won't be the right assumption. Provide you some benefits of the oxy-fuel combustion technologies. It's a very relatively straightforward process. It's very simple. The air separation unit, you have the boiler line, gas clean up, compression, and it doesn't have any impact on the steam cycle. So that's a big plus for the technology. And using existing power plant technologies, which are all finely tested components, it's the putting together of them into one process is what the challenge is technically. It can be retrofitted to existing plants or new builds. Doesn't have a big impact on the boiler thermal performance, even if you're operating in an oxy-fuel mode. And to make things clear, any boiler that was designed for air firing can operate under oxy-fuel without major pressure part modifications, but that needs to be taken into account as we need to perform detailed analysis to make sure that you don't cave the components of the boiler. It has the potential to avoid using an FGV or an SCR. What that statement basically means is not that you shouldn't have an FGV or SCR. If you're operating under an oxy-firing mode all the time, then you have a chance of avoiding the FGV or the SCR. But if you're designing the plant for oxy and air firing, you would need the SCR and FGV for your emissions. Can be designed to fire a wide range of fuels, and when I mean wide range, it does mean a wide range. In comparison to other technologies such as IGCC, you have an operation envelope which is relatively small, but for oxy-fuel combustion and for post-combustion capture, you have a very large operation envelope on the fuel boiler. The costs are comparable to any other of the CO2 capture technologies, and I mean capture, not only as compensation or storage in the same way. But the key points that are required for the success of this technology is its demonstration and proof of the burner and the thermal performance of the boiler on a larger scale. I'll go through the steps that we've taken to start from a very small scale to a reasonably bigger scale that we've come to, but as always, you need to work on a large scale to understand and provide more confidence on the commercial terms that you offer. This is, let's say, the heritage of oxy-fuel development in our company. We've been working on this for the past 20 years. 92 was a time where not a lot of people were thinking about carbon capture, but we've always had something in our mind. Even though we've done it at a very small scale, it was the largest in Europe at that time. And at that time, the company was also situated in a very small facility. So we retrofitted the existing burner testing facility for oxy-fuel firing, and then we basically hung fire on the development because we know that it was technically viable. We needed the interest in the community, in the market to actually come out for us to develop it more. So during that time, what we've been doing is performing validation studies, refining the design tools, performing engineering developments, etc. And then in 2008 to 2010, with the assistance of DEC, which is Department of Energy and Climate Change, received a grant to actually perform a full-scale demonstration. This to actually revamp our demonstration facility to burn a 40 megawatt thermal boiler burner. And then last year and this year, the part of this year, we used a 30 megawatt burner that we made basically based on the same parameters of 40 megawatt burner, just size it low to test it at Schwarzpumper. Schwarzpumper is the one that John had mentioned yesterday morning, where we're testing the oxy-fuel technology in an integrated form. As I said before, this section of the slide is basically to provide a background of gas separation unit and the CO2 processing section of the oxy-fuel technology. This, as I said, this slide is basically taken from Air Products' presentation that they did last year with the permission of Vince Wade. So if you need to look at the full presentation, I can give you the link for where you can probably find it and get a copy of the presentation. The difference, what I found is when you're looking at it from a power plant perspective, 95% oxygen and oxygen seems to be very, very high because it is. But for a gas manufacturer, 95% is actually low, very low grade, because they're looking at 99.999%. So for them, it's a low purity gas, but for us, it's a perfect point to actually tap on. And we've been working with Air Products for about the past 20 years on working with this technology. So we developed a certain part of the process, and Air Products are developing their separation unit and the downstream CO2 purification and compression section. As you would expect, oxygen pressure will be low because the boiler operates at a lower pressure than the atmosphere to allow ingress and not egress so that we don't let CO2 going out. but you want to limit that so that the CO2 purity is higher. And because of the sheer scale of the power plant, the amount of oxygen that we need would be high. So the demand for that will increase. Typically, for a 500 megawatt plant, you need 10,000 tons per day of CO2. The rule of thumb is for a size of a power plant, you need 20 times the amount of oxygen, and because when you form CO2, you also get the same amount of CO2. So you'll be getting about 10 tons of CO2. Okay. For end products, there is no use for co-products, but for us it's perfectly fine. The section that Air Products have been working on is optimization of the air separation unit, because the more development and improvement you perform there, it will reduce the amount of energy penalty you've got and increases your net power for just to give you a feel for the different air separation processes that are currently existing: adsorption, vacuum or pressure, cryogenic distillation, and the new generation technologies, which is ion transport membrane. But the point that I want to highlight is the scale that you can actually get. So for the size of plants that we're talking about, you would look for cryogenic distillation, which probably feeds back a bit with what Francisco mentioned in the morning regarding startup frames for the distillation section. The ion transport membrane is a relatively new development. The energy penalty is projected to be much lower, but at the moment it's under development and you can get only about 100 tons a day. Just to give you an overview of the whole process, you've got the main boost air compression, the air cooling and pre-treatment section, then your actual cryogenic separation for separating nitrogen out, and storage before you go into your boiler. Just want to drive, because as you could see, you need compressors to run the air compression unit. So just want to give you a feel for the different kinds of compressors that are employed in this kind of a field, which is centrifugal and axial compressors. Depending on the total size of the air that you need or the oxygen that you need, you would employ either one or two or either of them, depending on how many trains you need for flexibility, etc. We'll talk about flexibility in a little way. What I want to also show is, if you have an air separation unit which can handle X tons per day of CO2 of oxygen, how much power does it actually take? These are more ballpark numbers to provide you a feel for. If you're looking for about 3,000 to 4,000 tons of oxygen, you can either employ 1 or 2 trains of centrifugal compressor or a single axial frame compressor. But the power requirement might be anywhere between 22 and 33. Same goes for the different options. So you have optimization parameter to work with when you're dealing with different cases for legacy and not. Regarding the flexibility, because the process will be limited by the turn down on the compressor, and the compressor you can't turn down lower than 75%. On the boiler idle side, we've tested our burner to turn down to 40%. So if you're running your boiler at a 40% load, you can't expect your compressor to be doing 75%. So what you can intentionally have is multiple trains, so that it gives you a flexibility of bringing them into service and or taking them out of service, similar to those that I use in an conventional power plant, so that you have a feel for the freedom of choosing what size you want to run based on the peak conditions, your commitment to national grid, cost, any of the number of parameters that you're running. Just a quick slide to show you the CO2 purification process, which is Air Products CO2 purification process. I'll separate this out probably in the next couple of slides, but the main point what I want to drive out is the CO2 purification and compression process of Air Products. It has an integrated SOx, NOx, mercury, and SOx, NOx, and mercury removal as part of its process in the purification. Give you more detail. So the flue gas coming in goes through your start compression and Air Products is 8 acid gas column, where you remove your SOx, NOx, and mercury. unit that's basically to dry your flue gas much more, because you don't want water to be present when going for compression because of hybrid formation, which can cause major problems in blockage and pipelines. And then mercury removal is actually an integrated part of this. And then you go to a separation process, which is an auto refrigerator removal process, where you remove more oxygen depending on what your end product is. If you want to send your CO2 or EOR, you probably want to use an oxygen removal process at that end. And the gas from there, the target product CO2, goes to your air products is prism membrane section, which is a selective oxygen and CO2 selective membrane separation process. Then you have your off gas going to your atmosphere and your oxygen and CO2 rich back to your boiler. The point to note in this slide is the boxes that have been colored green are the ones that are commercially available at the moment. So no problem. The one that is in orange is the one where you need engineering data. The technology is fine to use engineering data, so it's technically viable. The one regarding the auto refrigerator oxygen, nitrogen, argon removal processes, it is a mature technology, but you still need data, as everybody will probably tell you for working on demonstrations, data, and more data, as long as you can validate every part of the process before. As I mentioned earlier, the SAR gas takes out the SOx, NOx, and mercury. What basically happens is your SOx gets converted to sulfuric acid, NOx into nitric acid, and then your mercury reacts with the nitric acid to be taken out. Oxygen removed if your product is for EOR, depending on the purity of the CO2 that you need for your product to sell. And then the CO2 oxygen recovery membrane technology, which has been tested and is one of their products' commercial offerings. This is a slide that kind of helped me understand how the NOx and SOx comes out, because I'm a chemical engineer, so I like chemistry. The NOx basically gets converted with reaction with water and oxygen to form nitric acid, and your SOx gets converted to sulfuric acid. The key point here that I want to show is the reaction rate that has been mentioned here. You've got slow reactions and fast reactions. If reaction is slow, it makes it your rate limiting step, so it's going to take a longer time for you to complete your removal. So you operate the SOx and NOx removal system at a higher pressure, because the reaction moves faster forward when it's at high pressure, and then you can actually cut down on residence time, which will benefit the overall optimization of your process. This is a schematic just to give you a bit more detail on the air process system. You've got your flue gas coming in, condensate being taken out, and then based on your SOx NOx removal, you remove your sulfuric, nitric, and your mercury. Then goes on for your condensation to remove water, because it's still got 25% water and you don't need that. Next, go on to remove any dilute nitrate that you get, and then if you notice, you're getting up to 30 bar in this two stages of compression. And for pipeline pressures, we need to go up to anywhere between 120 and 150, depending on which region of the world you are. This was a slide just I wanted to drive home a point. Something gets confused is regarding the purity of CO2 and the recovery of CO2. Purity of CO2 is different from the recovery of CO2. Purity is if you have 90% purity, which means you've got 90% of CO2 and 10% of any other compound that you've got, but if that's 90% recovery, what you're talking about is based on the feed gas that's coming in, or the raw flue gas that's coming in, you've been able to recover 90% of the CO2 from that. Okay. Compression options. I think Francisco mentioned very clearly earlier that in a carbon capture process, 70% of the energy penalty for the whole CTS goes in carbon capture. The remaining goes in transportation and storage. And compression to 30 bar or compression to 150 bar is not really a new concept. We've been doing that for a long time now, working to our pumping natural gas, etc. We're going to provide. So this is a mystery of technology, but there are incremental improvements that will be made there, which actually impacts the overall efficiency of the process. So that's the reason we are also working on carbon capture aspect of the process. And just wanted to give you a hint for the axial compressor that we're talking about for the commercially available system. Just wanted to give a picture for a 10-stage integrated unit compressor that we had a chance of working when we went to the Manthurbo's factory. They were using it for an EOR facility, and it kind of, when you look at it and they open it up, it kind of shows that it is a very, very intricate piece of machinery, but it's still tried and tested for so long. So they've got very, very tight confidence on the operation of the compressor. Okay, next, just want to give you the background of the oxy-fuel development that we have done in, and this is the scale that we did in the 92 to 95. The picture that's here, basically, probably not a lot of people know, but when we were working in 92, Mitsui Babcock or Babcock Energy at that time, we had a very small facility on High Street. High Street is basically one of the main roads in the town, so we didn't have a lot of space, etc. So in one of the docks or one of the manufacturing bays, basically just converted it into a test facility to test the concept of oxy-fuel firing at a 160 kilowatt thermal scale. And what we could find was the test went really well. As I said before, this was the first time it was done at this scale in Europe. And then it helped us learn a lot of operating lessons, which is very critical when you're trying to push a technology towards commercialization. The two main key points that I probably would want to touch on is the data that came from this test strip that you see was the first in the world for the industry to provide any data on slagging and fouling effects of operating on an oxy-fuel environment. And the same was, we were able to provide early data on the impact of fire, the impact of ash that comes from the oxy-fuel process on cement, on pozzolanic activity, basically cement production activities. And even at that time, 92, 20 years ago, we're probably proud to say that we had a very smooth transition going from air to oxy-fuel. And we learned a lot of valuable lessons, which we've made sure we don't repeat again, which would cost a lot of money. Just wanted to give you a schematic of the setup that we had, the test facility we had. I don't know if you'll be able to remember it, but if you won't, remember that name ERTF for tomorrow. Because what we did was this test facility, once we did oxy-fuel and when we worked on other things, then we were not satisfied with the small plant, we wanted to go for a big one. So we did the 40 megawatt thermal, which is another facility. And what we did was we used this facility and converted it into our post-conversion capture pilot plant, which we have run through. It's about a 1-month plant. I'll give you more details about that tomorrow. The schematic here basically is for the typical oxy-fuel plant. The difference that I just want to highlight is oxygen and CO2 are coming from storage tanks because it's a very small facility and was done years ago. One of the key slides from air products testing. This was on the ERTF as well. Air products have done a lot of work using simulated flue gas to demonstrate their NOx and SOx removal methodology, and they were successful at it. But this was the first time that they've ever done real flue gas, and what you basically see is the SOx and NOx conditions coming in to the rig, which is their test equipment, and leaving out at almost zero. So it was a very successful test for air products as well as others. Graduating one level higher, just want to share some pictures as well as some results from our oxy-fuel combustion system. Why did we need to do this other than government support to do it? we wanted to do a big scale project because as the case of any new technology, you need to go on a bigger scale to address a lot of issues. One of them is you can do a lot of techno-economic feasibilities, you can do a lot of theoretical studies, but unless and until you actually go and do it, you won't know the problem. And by doing that, what eventually happens is you start gaining a lot of experience and you implement it in any of your commercialization terms that you do. And as I said before, the other thing that we wanted to address with this test facility was to give more confidence to the utilities and the power plant operators regarding working in oxygen and CO2-rich environments. I'll show you the slide with all the collaborators and project partners who are part of this project. Majority of them were power plant operators and utilities. We want to get them on board so they understand that we're not using CO2 and oxygen at 75%, 95%. It's not really a major problem per se, but as with any gas or any toxic gas that you deal with, even flue gas for that matter, you have to take the precautions in place. The other sensitive motive, of course, is by doing this scale, only then we would be able to commercialize the technology. Just to give you a feel for who are the people involved in the project, Doosan Power Systems, we were the lead company for it. We have university participants as well, Imperial College and Nottingham. You'll see these university names coming again and again because we work with the universities quite a lot, which we use as an area for public knowledge dissemination as well. And they work on certain projects in their master's or PhD based on the project that we do. So it gives them a lot of real world experience. DEC, it was a supporting agency. DEC is one of the supporting agencies which has had a lot of support for carbon capture technologies overall. Scottish and Southern Energy is one of the leading power plant utilities in UK. And the other partners, E.ON, EDF, Waterfall, UK Coal, there was a coal for the testing plant, Drax, Dong, Airport, as I mentioned earlier, project partner and Scottish Power. So as you can see from the number of, the kind of project partners and collaborators we have, the idea was always, give them more confidence on the technology because that's how a new technology can actually graduate into becoming a commercial technology as long as if people just listen to it and just say, nah, it doesn't make sense. Even without understanding what it is, that's a loss by itself. And I hope that this program, after 3 days, you'll at least think twice before saying, oh, yeah, carbon capture is too expensive, too much of CO2 cost, etc. All of them are going to be part of any new technology. A schematic of our combustion test facility, we renamed this one as CCTF, which is Clean Coal Combustion Test Facility. Very similar to what you see before, but the main difference is we've got storage tanks here as well, but for oxygen, not for CO2, because you're actually burning and recycling the CO2 from the plant or from the combustion chamber. And then we've got our usual primary flue gas recycle, secondary flue gas recycle, coal, and this bit, which I don't know if a lot of people, sometimes I get questions about this. What are that? Basically, our cyclone separators for removal of particulates. Why did we use a cyclone separator, not an ESP? Is because, believe it or not, the test facility actually sits on the border of the Glasgow airport. So, right about 10 to 12 meters away from the compound wall of our test facility, you've got the runway actually coming in. You have the flights coming down. So, they had a height restriction issue. So, we had to go with a low section cyclone separators kind of an approach. And because this is a test facility, what we do is we don't transport or store CO2, we mix it with air and release it on the stack. With the composition very similar to what it would be if you do air fire, which is acceptable for a test facility according to Scottish Environment Protection Agency or SEMA, where we have to actually provide our emissions every quarter as to what we're putting out in the atmosphere. And one more important bit is that one there. It is a 90 megawatt thermal facility. When I mean 90 megawatt thermal facility, it is when we're doing other burner tests for full-scale conventional power plants. That's where we actually test our burners, which go with the power plants. And we don't do a size down, scale down approach or anything. We actually build the burner and go into the plant and we actually test it here. For the oxy-fuel, that's the 40 megawatt burner that we designed. Just wanted to give you a virtual tour, if you will, of the test facility. If you walk around, it'll probably take about 45 minutes in real life, but I'll try to do that in 45 seconds. This is the oxygen storage that I mentioned in the schematic. We've got the oxygen storage tanks and the vaporizers in the background. That's what that picture on your top right is what you see. That's your combustion chamber with your flue gas recycle coming in, and that's basically the burner. I'll give you a better picture of the burner. But that's basically the other side of the combustion chamber where you've got cameras to actually visualize the flame length, stability, etc. And this one, what you see in the left-hand bottom, is the oxygen control kit that Air Products have in place to ensure that we don't go more than what we need to on oxygen concentration. That's probably a better picture of the burner. And you've got another person standing there, so you know that that's the scale of the burner that we look at when we test it for the oxy-fuel burner. Just want to give you some very standard conditions. One key point is that the oxy-fuel burner is based or has been adapted from our Mark III low NOx axial spool burner, which was one of our major successful burners that we've sold all over the world. And it can be applicable for new builds or retrofits. The oxygen content of the primary gas is controlled to about 21 volume%. And as you can see, the overall stoichiometric ratio is controlled at 1.2, which is very similar to what you have there. And then, as I mentioned earlier, flue gas recycle rate is dependent on your flame adiabatic flame temperature and the furnace heat transfer, which is your convective heat transfer. I'll go on a little bit of basics at probably the end of the presentation to give you a feel for how do we choose the flue gas recycle ratio. Want to give you a bit about what were the kind of tests that we did with the oxy-fuel burner. This primarily concentrates on 3 different kinds of tests. One is isothermal testing to characterize the burner as in the flow split of the burner, the damper settings, and based on the results that we get from our test grid, perform CFD burner model validation as well, and any lesson that we learn from our CFD is actually fed back into the loop, and we do the testing. The next testing takes those lessons into the picture. And then, as you would expect for any burner test, we did burner cooling tests to prove and demonstrate that the flame was stable, it was operation, it was controllable, air to fuel, oxy-fuel transition was smooth, sure about that in a bit. And we were able to start off load change, as I mentioned earlier, because we turned down at about 40%, with no issues. The flame stability was perfectly fine, flame attachment was brilliant, no problems at all. And then we did a few parametric tests to test for the combustion efficiency and the emissions in the plant. That is basically one of the tests that we did on the whole burner, where we start, that's the flame that you see is when you start on the oil, when you start with the plant, and then you slowly produce a flue gas recycle. It's still oil air, but with flue gas recycle coming back, then you stop, bring the coal on, and then it goes on to full oxy-fuel transition. So from there to there, in a typical full-scale plant, it probably takes about 15 minutes on a full-scale plant. But for these tests that we've worked on, we've done it over a period of hours. We wanted to understand each and every stage, how it affects the burner, does it affect the burner, how well it supports itself. This is the turn-down condition test that I mentioned before. To be very honest, I've heard a lot of talk about, we've done turn-down tests before from a lot of our other competitors, but I've not seen any pictures or any results published. So we've been doing this for a long time, and we publish our results. Don't really mind. We've gone from the 40 megawatt scale up to 40% to 16 megawatt thermal scale. And as we think we've got a great product that people will be interested in. Just wanted to show you the NOx, SOx, and carbon and ash calculations for the oxy-fuel burner. What you see here is it's an ppm dry condition and NOx values. What you'll see is in the oxy-fuel oxy-firing mode, it seems like it's actually a lot more than what you see in the air-firing mode. But the thing that's NOx values going up. Similar results for SOx as well. It could be almost in the same realm or much lower depending on your condition that you're running it on. Carbon and ash, very similar to air firing, so they're not too far away. Just wanted to summarize the 40 megawatt thermal scale testing that we did. We've been able to successfully demonstrate that 40 megawatt thermal burner is possible, can